Welcome to my channel. In today's video, we will learn about PN Junction diode, the heart of modern electronics. If you are curious, stay tuned till the end of this video. I will break down concepts step by step, making learning simple and fun. So let's start. What is a PN junction diode? A PN junction diode is formed when a p-type semiconductor is fused to an n-type semiconductor. It creates a potential barrier across the diode junction. This is simple representation and electronic symbol of PN junction diode. It is referred to as a minority carrier device since its current conduction is controlled by the minority carrier diffusion process, which are electrons in the p region and holes in the n region. So, there are two types of PN junction diode, PN homojunction diode and PN heterojunction diode. So, what is a PN homojunction diode? If a PN junction diode is formed by using the same type of semiconductor material but with opposite dopant impurities in the p and n regions, it is referred to PN homojunction diode. For example, gallium arsenide diode laser. It is used in different applications, for example, laser printer, barcode reader, and fiber optic communication. The next type is formed by using two different types of semiconductor materials with different band gap energies and opposite dopant impurities. In this case, we call it as PN heterojunction diode. It is usually made up from the compounds belong to second and sixth group, and sometimes the element compounds from third and fifth group. So how it works? Before diving deep, let's see what is n-type and p-type semiconductors. In pure form, they are intrinsic semiconductors. In n-type semiconductor, which is usually doped with the group 5 elements, where pure semiconductor, for example, silica or germanium, they make covalent bonds with pentavalent elements to form extra electron. And in this way, in n-type extrinsic semiconductors, there are extra electrons. On the other hand, in p-type extrinsic semiconductor, the pure semiconductor is doped with elements belong to group third, which are trivalent, and they keep a void or hole open, which makes holes abundant in p-type of semiconductors. So this is a diagram where the junction is in unbiased form. In p-type, there are majority carriers which are holes. In n-type, there are majority carriers which are electrons. In this slide, we will discuss about the biasing in PN junction. So we have three conditions. The first is no bias, then the forward bias and the reverse bias. So when there is no external potential applied to the junction, consequently, there is no external potential, different components of charge carriers could be transported in both regions. And there are two types of majority carriers, electrons in n-type and holes in p-type. Same for the minority carriers, electrons in p-type and holes in n-type. Due to gradient in the carrier concentrations, the majority carriers will diffuse in the opposite direction, and this process is called diffusion. The minority carriers will drift towards the p region and also the n region. This process continues until the system achieves a thermal equilibrium. A depletion region is formed which is fundamentally free of charges, and an electric field occurs in the interface between them. Due to this electric field, a voltage is rising, and this is known as built-in potential voltage. I think this is the basic theory of no biasing, and now we move forward to the forward bias condition of PN junction. In this case, a positive voltage terminal is connected to the p-type region and a negative voltage terminal is connected to n-type region. In this case, depletion region becomes narrow. The reason is majority carriers. Due to same charges repel phenomena, these carriers are forced to diffuse in opposite direction, which makes the depletion region narrow. In case external potential is higher than the built-in potential, a forward current flows through the circuit. And this graph represents the current voltage characteristics of forward bias PN junction diode. We have marked 3 points A, B and C. So, at point A, the forward current is 0 at 0 bias condition. At point B, the current increases slightly until it reaches approximately 0.7 volt at the knee of the curve. And after point B, the change in the forward voltage is not so visible. And at point C, the forward current increases rapidly. The forward voltage at the point C is approximately equal to the built-in voltage. So this is the condition of forward biasing. Let's move to the reverse biasing. In reverse bias, the positive voltage terminal is connected to N-type region and the negative voltage terminal is connected to P-type region. So what happens in this case? The depletion region becomes wide and the applied potential is less than the built-in potential. The minority carriers will be drifted towards P-type region and this process continues until again the thermal equilibrium occur in the both sides of the junction. This bias gives rise to increased thickness of depletion region. As I told, depletion region became wide. A very small current can pass from the N-type region to P-type region, which is referred to as reverse current. And as we can see, the voltage current characteristic in this case, at zero bias condition, the reverse current is strongly vanished. If the reverse bias voltage is increased, a very small reverse current is seen. The reverse current increases rapidly when only the applied voltage exceeds a certain value, which is called as breakdown voltage. So in this video, I have explained the theoretical concepts about PN junction, its definition, its types, how it works in different biasing conditions. In the next video, we will discuss about all the mathematical phenomena of PN junction diode. If you like this video, you learned something, please subscribe it. If someone wants one-to-one class or PDF notes regarding any topic related to PN junction diode, please follow me on LinkedIn and you can contact me there. Thank you so much for watching this video.